Hydrogels are water-absorbing polymers capable of holding large amounts of water relative to their weight, making them highly valuable in agriculture. These materials act as reservoirs, releasing water slowly to plants over time, which improves soil moisture retention and reduces water wastage. Hydrogels can also be infused with nutrients or fertilizers, delivering essential compounds directly to plant roots in a controlled manner. For example, in arid regions, hydrogels mixed into the soil help sustain crops by storing water during rains and releasing it during dry periods. In greenhouses, hydrogels reduce the frequency of watering by maintaining consistent soil hydration, helping delicate plants thrive. Hydrogels are also used in seed coatings, ensuring seeds remain hydrated during germination, even in challenging conditions. Additionally, they can be applied to vertical gardens or rooftop farms where water retention is critical. By improving water efficiency and soil health, hydrogels offer a sustainable solution for combating drought, enhancing crop yields, and reducing irrigation costs, making them a transformative tool in modern agriculture.
Hydrogel agriculture is an innovative approach that uses water-absorbing materials known as hydrogels to improve soil moisture retention and support plant growth. Hydrogels are polymers capable of absorbing hundreds of times their weight in water, transforming liquid into a gel that can be stored within the soil. These materials are particularly effective in arid and semi-arid regions where water scarcity limits agricultural productivity. By retaining water and releasing it gradually to plants, hydrogels reduce the need for frequent irrigation, improve soil structure, and minimize water loss through evaporation and leaching. This technology is gaining attention as an eco-friendly solution to challenges like drought stress, soil degradation, and desertification. The use of hydrogels aligns with sustainable farming practices by conserving water resources and enhancing crop resilience under harsh environmental conditions. Example: in sandy soils where water retention is typically poor, hydrogels can increase water holding capacity by up to 85%, drastically reducing the frequency of irrigation. Analogy: hydrogels act like tiny reservoirs hidden in the soil, storing water during rainy periods and slowly releasing it to plants when needed. Hydrogels are three-dimensional, hydrophilic polymer networks capable of absorbing and retaining vast amounts of water relative to their weight. These polymers expand when hydrated, locking water molecules into their structure through hydrogen bonding and capillary forces. Hydrogels come in various forms, including synthetic polymers like polyacrylate and natural materials like starch-based hydrogels. Hydrogels differ in their water-holding capacities, biodegradability, and environmental impact. Starch-based hydrogels are eco-friendly and break down naturally in the soil, while synthetic hydrogels like cross-linked acrylic acid polymers are more durable but may release harmful byproducts as they degrade. The type of hydrogel used depends on the specific agricultural need, such as increasing water retention, reducing fertilizer leaching, or delivering agrochemicals. Biodegradable starch-based hydrogels can retain significant amounts of water while decomposing naturally, making them suitable for environmentally conscious farming practices. Hydrogels are like sponges embedded in the soil, soaking up water and holding it in reserve until plants need it. Incorporating hydrogels into soil significantly improves its physical and chemical properties, making it more suitable for plant growth. Hydrogels increase the soil's ability to retain water, reducing water loss through evaporation and deep percolation. They also improve soil structure by reducing compaction, enhancing aeration, and allowing plant roots to grow more freely. Furthermore, hydrogels enhance soil permeability, ensuring that water infiltrates evenly and reaches plant roots effectively. They also reduce the leaching of essential nutrients like nitrogen and phosphorus, ensuring these nutrients remain available for plant uptake over extended periods. This minimizes fertilizer waste and reduces environmental pollution. A study demonstrated that hydrogels mixed into sandy loam increased its water retention by over 5%, helping crops survive during dry periods. Hydrogels are like a soil conditioner, transforming hard, dry ground into fertile, moist land suitable for cultivation. Desertification, characterized by soil degradation and loss of agricultural productivity, poses a major challenge in arid and semi-arid regions. Hydrogels provide a promising solution by improving the soil's capacity to retain water and nutrients, even under extreme conditions. By reducing water stress and promoting plant growth, hydrogels can help restore degraded lands and combat desertification. Hydrogels also protect soil from erosion by maintaining its structure and reducing runoff during rainfall. This stabilization effect prevents further loss of fertile topsoil, enabling sustainable farming in regions previously deemed unsuitable for cultivation. In India, hydrogel treatments have enabled farmers to cultivate crops in regions affected by desertification, conserving water and boosting agricultural productivity. Hydrogels are like lifelines for drought-stricken lands, rejuvenating barren soils and enabling the return of vegetation. Hydrogels can be engineered to encapsulate pesticides and fertilizers, allowing for their slow and controlled release into the soil. This ensures that agrochemicals are delivered precisely where and when they are needed, increasing their effectiveness and minimizing environmental pollution. For example, hydrogels can be loaded with herbicides or insecticides that are released gradually over weeks or months, providing long-term protection against pests without the need for frequent applications. Similarly, hydrogels encapsulating fertilizers reduce nutrient loss through leaching and ensure plants receive a steady supply of essential nutrients for optimal growth. Example: a hydrogel system using polyvinyl alcohol can release phosphate fertilizer slowly, improving nutrient availability in sandy soils and boosting crop yields. Analogy: hydrogels are like time-release capsules for the soil, delivering nutrients and protection steadily to support plant health. 6. Hydrogel agriculture and sustainable water use. Scientific explanation. Water scarcity is a growing concern in agriculture, particularly in regions with limited freshwater availability. Hydrogels address this issue by significantly reducing the frequency and volume of irrigation required for crops. They absorb excess water during periods of rainfall and release it gradually during dry spells, ensuring consistent moisture availability for plants. Hydrogels also reduce water loss through evaporation and infiltration, maximizing the efficiency of irrigation systems. By conserving water and reducing dependence on external water sources, hydrogels contribute to sustainable farming practices and help farmers adapt to changing climate conditions. Example: farmers using hydrogel treatments in sandy soils have reported up to a 50% reduction in irrigation requirements without compromising crop health. Analogy: hydrogels are like water banks, storing and releasing moisture as needed to sustain crops through droughts. Biodegradable hydrogels, made from natural materials such as starch or gum tragacanth, offer an eco-friendly alternative to synthetic hydrogels. These materials decompose naturally in the soil, leaving no harmful residues, making them ideal for sustainable agriculture. Unlike synthetic hydrogels, which may release toxic byproducts like acrylamide during degradation, biodegradable hydrogels are safe for the environment and help maintain soil health. They can also be tailored to specific agricultural needs by adjusting their water retention capacity and decomposition rate. Example: a starch-based hydrogel was shown to increase soil water retention while breaking down into harmless organic compounds, improving both crop growth and environmental sustainability. Analogy: biodegradable hydrogels are like compostable containers. They serve their purpose and then return to the earth harmlessly. Hydrogels are becoming commercially available for a wide range of agricultural applications, including horticulture, landscaping, and large-scale farming. These products are designed to enhance crop yields, conserve water, and reduce the environmental impact of agricultural practices. Government and research institutions are actively promoting hydrogel technologies to address food security and sustainability challenges, particularly in regions vulnerable to climate change. The development of cost-effective, scalable hydrogel solutions is a key focus of ongoing research and commercialization efforts. Example: the Indian Agricultural Research Institute, IA, developed a hydrogel product to help farmers in drought-prone regions, improving water efficiency and crop resilience. Analogy: commercial hydrogel products are like advanced farming tools, making agriculture more efficient and environmentally friendly. The future of hydrogel agriculture lies in developing advanced materials with improved water retention, faster biodegradability, and multifunctional capabilities, such as nutrient delivery and pest control. Emerging technologies, such as nanotechnology and bioengineering, are enabling the design of smart hydrogels that respond to environmental cues like temperature or soil pH. These innovations could revolutionize agriculture by making crops more resilient to drought, reducing reliance on chemical fertilizers, and enhancing soil health. As climate change intensifies, hydrogel agriculture will play a crucial role in ensuring global food security and promoting sustainable farming practices. Hydrogels incorporating nanotechnology are being developed to enhance their efficiency and adaptability for precision agriculture. The future of hydrogel agriculture is like upgrading from basic irrigation to intelligent, climate-adaptive farming systems.